Hello, my name is Georgi Radov, and in this video I would like to discuss the concept of poles and zeros from the perspective of electronic circuits. By the end of this video, my aim is that you are able to construct the linear transfer of systems, linear systems that are given with certain sets of poles and zeros, and then construct their Bode plots, their linear amplitude transfers and their phase transfers. So let's begin. The approach that I will follow is bottom up. I will start with simple circuits such as the RC stage and the CR stage, and based on these examples I will define the concepts of poles and zeros. Then I will generalize to a generic system with a random number of poles and zeros. Here a RC stage is given, so this is really very basic, and such circuits occur very often in electronics. Then we have an input, and then a capacitor is being charged through a resistor. The output is taken on the plate of the capacitor. Then if we have a signal applied at the input, there is a potential difference created across the resistor, so current flows, and the current is terminated on a capacitor. So charges appear here that actually change the voltage on the capacitor, and this voltage is actually the output voltage. So there will be certain signal here. Since this is a linear circuit with linear components, a resistor and a capacitor, the expectation is that if you apply a certain tone with frequency omega, then you have at the output the same frequency omega, but then with different amplitude and also different phase. So let's see how it works. Now, from the definition of a capacitor, that a capacitor is the QdV, so the change of the charge for given change in voltage. And the other definition, fundamental definition, is that the current is the flowing time of charges. So the current is the QdT, the amount of charges that flow for given time dt. If you combine both, you'll get the basic equation of a capacitor, which is that the current through a capacitor in time is the capacitive constant C dV dt. Or if the voltage needs to change more, you need more current. Then we note that the current through the resistor is equal to the current of the capacitor. The current through the resistor is V in minus V out divided by the resistor R. So it's given here. And we equate this current to the current of the capacitor to get here this equation. And from here, reordering the terms, we can express the input voltage as an output voltage, the RC constant, and the derivative of the output voltage in time. Now, this is a simple differential equation which we can solve. We just put this in Wolfram alpha and we get the answer. So, and the answer looks like something like this for a sine wave signal. So say the input voltage is a sine wave signal, something like this. Yes. The RC constant, so the product of the resistance that we have here, and the capacitor is the time constant. We define it as tau, the time constant. And then solving this simple first order linear differential equation produces an answer which is given here. Let's see what we have. So this is at the input a sine wave with certain frequency omega. At the output we have two components with this frequency. So you see that the frequency did not change because it is a linear system. And we have also this term. So now let's handle this term first. This has to do with the settling. So this term is important for DC signals. You can see that if t goes to infinity, so we consider a steady state solution, this will go to 0. So the signal at the output will settle. So this we'll ignore for a while, then later we can see what exactly is this constant C1, but for the moment it's not important. If we consider a steady state signal, so such as sine wave, then we will deal with these two terms. So what we see here is that the output signal, V out, will be something between sinus and cosinus. This means that there will be a certain phase shift, which will be from 0 to minus p over 2 to minus 90 degrees. And now we can also reason at what frequency it will be closer to sinus and at what frequency it will be closer to cosinus. So if omega is small, say very close to 0, then you can see that this term will be gone because of this omega here in the denominator, in the nominator. So the output will resemble much more sinus. And indeed, if this is very small, the output will be just sinus omega t, or the output will follow the input. Indeed, you see if the capacitance is if the frequency of the signal is very, very slow, then the capacitor has enough time to collect these charges here from the resistive current and change its voltage so that it follows the input. Now, if omega is very high, then you see that this term here, so let me erase. So you see that this term here will be dominant because of this omega here. Yeah? So the output will resemble much more cosine, or there will be a minus 90 degrees phase shift. What we also can say about the amplitude is that the amplitude of the output signal will be very small because of this term here. If this omega in the denominator is very high, all this will scale down in amplitude. So there will be a phase, there will be a shrink in amplitude, and there will be a phase shift. Now you see that the evaluation of the output in time domain is given here for different input frequencies. So the input is still sinus So the input is still here, a sinus omega t. And then if omega is very small, for example 0.1 over tau, so then this here is not dominant and this is very small, so this makes it 0. We ignore this term. Then the output is almost a sinus, and you can see here how the output follows the input. On the contrary, if the output is if the input frequency is very large with respect to tau, then this here is big number and this here is big number, so both terms become very small, hence the amplitude is shrinked, what we see here at the output. Then this here will scale up the second term and it will become dominant over the first term, which means that also the signal will experience this delay in time, or a phase shift of minus pi over 2. Now, very interesting is to examine what happens in between when the frequency is exactly equal to 1 over tau. Then the amplitude will be reduced a little bit and we can calculate exactly what by what amount it is reduced, and then the phase shift will be somewhere in between 0 and minus pi over 2. So then we consider the special frequency omega, called minus 3 dB frequency, and we'll see why, which is equal to exactly 1 over tau, where I remind you that tau is the product R times C. So if we plug in this omega here and here, we ignore this settling term, then the output will be exactly this. It is plotted here, and then you can also see the amount of attenuation, that if this is scaled, the input is scaled to 1. Here we have a level of about 707. Why is this number? We can get it from here, but we can also see when we evaluate, analyze this RC group in frequency domain. This is analysis in time domain. Now, in frequency domain, the analysis uses the S domain, or Laplace transform. So then we assume that the voltages and the currents are complex numbers of the type AEST, where the operand S is a complex operand with certain real part sigma and j omega, imaginary part. Now you can see that if sigma is 0, then S becomes j omega, and this is the case when we consider steady signals, so basically tonal signals with constant amplitude. If sigma is negative, then we will have signals with exponentially declining amplitude, and if sigma is positive, we will have signals with exponentially increasing amplitude. Here in our analysis we are interested in the special cases when sigma is 0. We have signals that are constant in amplitude, tonal signals of the type exponent on a power of j omega. So for these signals, we can reconsider the equations of the capacitor. So we started with that the current is the capacitance dVdt, and then you see here if the voltage is of the complex type amplitude and certain EST. When it is in the derivative, the exponent is very easy to calculate because it is the same exponent and the operand s comes in front of the derivative and it multiplies the capacitance. Then the current is also complex of the type I, the amplitude, and exponent on the power of st, showing the frequency of the signal. And if we combine this in this equation, we have that the voltage is equal to the current times 1 divided by SC. Now, this equation resembles very much the equation that we have for resistors, the Ohm's equation. Instead of resistance, we have here impedance, and the impedance of a capacitor, which is 1 divided by SC. If you consider now the operand S being only j omega, you'll see that for low frequencies this impedance is very high, and indeed the capacitor acts as an open circuit for very low frequencies, while for very high frequencies in the denominator we will have the frequency and it will be very high, so the whole impedance will be very small. And indeed the capacitor acts as a short circuit for very high frequency signals. Now, with this complex representation of the impedance of the capacitor, we can calculate the transfer characteristic of RC group in the S domain. So giving something like this. The resistor and the impedance of the capacitor form a voltage divider. The current is common, so you can equate the resistive current and the capacitive current, and the resistive current is simply V in divided by the impedance to ground, so it will be V in divided by R plus 1 over SC, and the output voltage will be V out divided by the impedance to ground, which is 1 over SC. You equate the current and you get the output voltage in S domain, or you get here the transfer characteristic in S domain. Now, so we have here, so you can see it is 1 plus S tau, where tau is the time constant equal to RC. To evaluate the signals, you substitute S with j omega, sigma is 0, and the transfer characteristic in frequency domain becomes 1 divided by 1 plus j omega RC. Then this transfer characteristic has certain amplitude transfer and phase transfer. Amplitude transfer shows what will be the amplitude of the output signal in relation with the amplitude of the input signal, or in this case we will see how much the output signal will be attenuated. And to do this we need to take the magnitude of the transfer characteristic, and you take the magnitude of a complex number by square root of the power of its real term plus the power of its imaginary term. So the real term here is 1 and the imaginary term is this, and here it is calculated 1 divided by square root of 1 plus omega squared tau square. To evaluate the phase shift, we take the argument, and the phase shift will be arcus tangens of the imaginary part divided by the real part. Now let's consider what this will be for very small frequencies. So this case here, which we had from the time domain analysis. If the frequency is very small, then this term can be neglected because 1 will be dominant. And then the magnitude transfer is almost 1. And we see indeed that for small frequencies, with respect to the tau, the amplitude does not shrink very much. Now, for high frequencies, so if omega is very large with respect to tau, then this term becomes dominant, much higher than 1, and we can ignore the 1. Then the transfer becomes simply 1 divided by omega tau. In this case, the denominator will be large. We will have 1 divided by a large number, so the transfer will be very small. And indeed, we see that for high frequencies, the amplitude is shrinked down. To evaluate the phase transfer, we have to take the imaginary part and divide it by the real part. Let's see this for the special frequency of minus 3 dB, or 1 over when omega is equal to 1 over tau. Then we can substitute it here, and we will see that the transfer, so this will be equal to 1, so it will be exactly equal to this real part, and then the amplitude transfer will be 1 divided by square root of 2. Hence, the transfer of 0.707 here. So if you see here, it is 0.707. Now, if you take this linear transfer in logarithmic scale in dB, so you'll take 20 logarithm of this number, you will see that it is almost equal to minus 3 dB. And indeed, this gives the name of this special frequency as the minus 3 dB, or the corner frequency. So we say this corner because this part, the frequency dependent part, is exactly equal to 1. For frequency lower than this, we can ignore this part and we can assume that 1 will be dominant. And for frequencies that are higher than 1 over tau, then this term will be high and it will be dominant over the 1, and we can ignore the 1. So we will have a transfer of 1 divided by omega tau. Now, for the phase shift, or the argument of this complex transfer, we have to take the imaginary part and divide it by the real part. For this, we will so first substitute omega with 1 over tau in the equation. So we will get this. And we have to now isolate the real part and the imaginary part, which is this arithmetic here. So if we take the real part and divide it by the imaginary part, we have an arcus tangens of minus 1. And indeed, this is minus pi over 4. Or in other words, exactly at the corner frequency, the phase rotation is equal to minus 45 degrees. I remind you that for low frequency, the phase rotation is small because the output follows the input closely, so phase rotation of almost 0. Then at the minus 3 dB frequency, or when omega is equal to 1 over tau, the phase rotation is minus 45 degrees. And at very high frequency, the phase rotation is minus pi over 2, or minus 90 degrees. So this can be represented graphically in the S domain. So in the S domain we have a real part, which is the sigma, and imaginary part, which is the j omega. The transfer that we have of the RC stage can be represented as 1 divided by 1 plus S tau, where S tau is, I remind you again, R times C. So we will reform it a little bit in a way that we can see directly the roots of the denominator. So this will be this arithmetic, and then the transfer characteristic of the RC stage in S domain is 1 divided by tau times S minus SP, where SP is the pole, and this solution of the denominator, the root of the denominator, for which the expression HS explodes. We divide by 0, so it will be a transfer of infinity. Now this will be then the root of the denominator will be the pole, and we can literally plot it. We can position it in the S-plane. So in this case it will be the solution of the denominator, or the root of the denominator, is 1 minus tau. It is here. Now we want to evaluate the transfer for certain signals, and these signals are with constant amplitude, and the signals with constant amplitude are on the y-axis, the j omega axis. So this will be then the DC signal, and as we go higher and higher, it will be signals. These will be signals with higher frequencies. So now what we can see is that if we increase the frequency, then the denominator increases, so the transfer decreases. Then let's see how it works graphically. Say we have here a frequency, low frequency, omega 1, and we want to know what is the amplitude transfer. To calculate the amplitude transfer, we have to divide by the distance that we have between the frequency for which we evaluate the transfer and the actual pole. And this is actually the magnitude, because we have the imaginary part here and we have the real part here. So this will be then the modulus, and we have 1 over tau from this transformation, and then P1 will be then Pythagorean theorem imaginary part square and real plus real part square, and then square root of it. So this will be this vector here that we will see. So this is the vector P1. Yeah? So you see that vector P1 is almost equal to minus 1 over tau, a little bit smaller, so there is a little bit of attenuation for this frequency. And you also can see that for 0 frequency, so for DC signals, P1 is equal to minus 1 to 1 over tau, so the transfer is 1. Then also what you can see is if you evaluate a very high frequency, a frequency which is somewhere here, then this vector P will become very, very high, so infinity. And then the transfer will be 1 over tau divided by infinity, or something very, very large, so the transfer will be small. Then to evaluate the phase shift, we need to take the Arcus tangens. And this is actually this angle here that you have, this actor, this angle here, alpha, taken of course with the negative sign. So for very small signals, this angle alpha is very small, hence the phase shift is 0. The output follows the input. However, if the frequency of the input signal is very high, this angle will become almost 90 degrees, which is the minus 90 degrees phase shift. And then for frequencies which are in between, you have, of course, less attenuation and less phase shift. Of course, now we can plot the amplitude transfer and the phase transfer. So we see here the amplitude transfer for low frequencies. It is almost 1 because this vector here is almost equal to 1 over tau. For very high frequencies, this vector becomes much higher than 1 over tau, and then the transfer is very small. So this is the transfer in between. Of course, interesting is the corner frequency when omega is equal to 1 over tau. In this special case, you can see here that we have 1 over tau here, 1 over tau here, because this is a unit circle, and hence this vector will be simply 1 over tau square root of 2, and hence we'll have the 3 dB. So this will be, if you normalize it, here you see the 0.707 transfer. Now for the phase response, you look at this angle. This is the arcotangents of the imaginary part divided by the real part. For small small frequency, it's the angle is very small, and exactly at the corner frequency we have phase shift of 45 degrees, or minus pi over 4. And then for very high frequencies, this angle becomes minus 90 degrees, or the phase shift gets minus pi over 2. Now we can go back to time domain and then cross-check the analysis that we did in the frequency domain in the S-plane with the result that we had in the first slides in, analysis in the time domain. So in our analysis in time domain, we assumed a sine wave input. To get to S domain, we need to make a Laplace transform of the sinus omega t, and this is the Laplace transform. And now the output voltage in S domain can be directly calculated as the input that we apply times the transfer characteristic in S domain. So you have these two, and then this is the output in S domain, and you can run inverse Laplace transformation of this expression to get the result in time domain. And if you run it, for example, in Wolfram alpha, you get this result. And this is exactly the analysis that the result of the analysis that we did in time domain. And here we have also the settling constant C1. Now, what we see so far from this RC stage, this simple example, is that every combination, every RC stage introduces one pole in the signal path. And this pole is first of all negative, and it is real, and it has the following effects on the signal. It reduces its amplitude. For low frequency less, for high frequency more. For frequency, which is called a corner frequency, in equal exactly of 1 over tau, where the tau is the RC product, this transfer, the transfer or the effect of the pole on the signal transfer is in the amplitude 0.707, so we shrink the amplitude. The pole also causes phase shift of the output signal with respect to the input signal. For low frequency, this phase shift is less. For very high frequency, it can go up to minus pi over 2, whereas exactly at the corner frequency equal to 1 over tau, this phase shift is minus pi over 4 or minus 45 degrees. Now let's introduce the concept of zero. And for the concept of zero, we'll consider the CR stage. So now we swapped the capacitors and the resistor. So now what you can clearly see that the transfer for DC signal is zero, because for DC signal the capacitor acts as an open circuit. There can be no DC current flowing through the capacitor. So this means that now the transfer for very low frequency is very, very small. Then for very high frequencies, the capacitor will act as a short circuit and the output will be shorted to the input. So the output will follow exactly the input. Now let's understand this transition from open circuit to short circuit of the CR stage, and let's see what happens with the phase transfer and how the CR stage introduces a zero in the transfer characteristic. So now you know the impedance of a capacitor being 1 over SC, and you can express the output in terms of the input and the capacitor and the resistor, considering that the capacitor and the resistor form an impedance voltage divider. So Vin divided by the impedance plus the impedance of the capacitor plus the resistance will give you the resistive current, and it is equal to the capacity will give you the resistive and the capacitive current. So basically this is the same current, and you can express the same current also as V out divided by R. When you equate both, you get the transfer characteristic of in S domain. So we see in comparison with the RC stage that the denominator is the same, but in the numerator we have this expression ST. So we clearly see that now we have also a zero. This is the root of the numerator. This is the value of S for which the transfer becomes zero. So we have the zero in the origin. Here is the zero of the CR stage. And we have, of course, the pole that we just discussed. So now here after this transformation we see clearly the zero at the origin and the pole equal to SP or 1 over tau. Now let's consider how to evaluate the transfer characteristic in magnitude. In magnitude, we for a given frequency that we want to evaluate, omega 1, we have to consider the distance between the zero and the pole, and then the ratio. So basically, for DC signals, the signals that we evaluate exactly overlap with the zero, so the transfer is zero. This was expected. But now for AC signals, we will have non-zero transfer. So for example, omega 1, we will have the vector Z1. So this will be in the numerator here. divided by the vector p1, so divided by this. So this will not be 0, it will be something very small. And as we increase the frequency, so basically we go higher and higher in the y-axis, you see that the z vector increases, and at certain moment it starts becoming comparable with the p vector, and they cancel each other, and we have transfer of 1. So you can see this at this border at the corner frequency, or the frequency equal 1 over tau, or the frequency of the pole. So this is this frequency here. Then you can calculate what is the transfer. So first you have the 0 vector, which is this one, 1 over tau, and then you have the pole vector, which is this one, which is square root of 2 divided by tau. The 0 vector is 1 over tau. Then when you put the 0 vector and the p vector here, you get the transfer of 0.707, the corner frequency. For the phase shift, you have to consider the phase shift due to the 0 and the phase shift due to the pole. So to get the argument of this transfer characteristic, when you substitute the operand s with j omega, then you just reform this expression that you get, so that you isolate the imaginary part and the real part, and then the argument will be arc costangens of the imaginary part divided by the real part, or 1 over tau divided by omega. Now what you see is basically that you have to take the angle of beta. So this is the angle, this one, that is due to the 0, and you substitute the angles of alpha, or the sum of the angles of alpha if you have multiple poles. So then you have, even for very small frequencies here, pi over 2 phase shift. So you start with pi over 2 phase shift, and then you substitute alpha, and as frequency increases, this alpha also increases. So until it becomes here 90 degrees. So at very high frequency you have 90 minus 90 equal to 0 degrees phase shift. So indeed you can now get the Bode plots at very low frequencies. The transfer characteristic will be 0, because these frequencies are very close to the 0. As you increase the frequency, you move away from the 0. So then you have here increase in the transfer. If you take, this is in linear scale. If you take it in dB scale, or you take 20 dB per decade, you will see an increase of plus 20 dB per decade. And you have this increase almost when you reach the pole frequency, where this is this frequency, in which both vectors, the z vector and the p vector, become comparable, and they cancel each other, and then you have a constant transfer. For the total phase shift, you have the contribution of the 0, which is 90 degrees, or plus pi over 2, and then substitute from it the contribution of the poles. As you increase the frequency, the contribution due to the pole will increase. So you see that the contribution of the pole is with negative sign, and then from pi over 2, you start substituting until both angles for very high frequency become comparable, equal to 90 degrees, and they cancel each other, and you have 0 phase shift, or the output follows the input. Exactly at the corner frequency when omega is equal to 1 over tau. The phase shift is pi over 4. Now let's generalize now for a system in which we have many zeros and many poles. So if you evaluate this ratio in the logarithmic scale, in dB scale, you need to take 20 logarithm of the magnitude. So you have the DC transfer, of course, and then the contribution of each zero here will be plus 20 dB per decade. The contribution of every pole will be attenuation of the signal will be minus 20 dB per decade. Why is this 20 dB? So you can see here from this expression that if you have reached a certain pole worth 0, this omega becomes comparable to tau, and then this whole term becomes comparable to this one. For frequencies that are less than the pole or the 0, this 1 over tau, 1 will be dominant, and then we can ignore this term. Or for frequencies which are greater than 1 over tau, or the pole and the 0, then this can be ignored because this will be much larger than the 1. And then there will be this contribution of 20 dB per decade, because if you ignore this, you can see that this 20 comes here. Then for the argument, if we represent the numerator and the denominator in this generic expression as complex numbers with a and b and c and d, then the phase shift or the argument will be the arc costangens of b divided by a, or the phase contribution of the zeros, minus the phase contributions of the poles. So now let's consider an arbitrary system and some exemplary Bode plots, magnitude response and phase response. Let's assume now that these zeros and these poles are distributed in this way here in the frequency domain. So for very low frequencies, we do not feel the influence of any pole or any zero, and the transfer is simply here the DC transfer H0 that we start with. As we increase the frequency, we reach our first pole. So this pole is at lowest frequency. And then first we'll feel the rotation of the phase due to this pole. And the total contribution of this rotation will be minus 90 degrees. Exactly at the pole will be minus 45 degrees, or minus pi over 4. So this will be this. After these frequencies, we will have a steady decline of the amplitude transfer of minus 20 dB per decade, and because this term will be more dominant than this, so we can ignore this one. For the other terms, this term, and this term, they will be less than 1, so here we will have 1, 1, and 1, and then the transfer, the total transfer, will be dominated only by this term, and hence we will have the minus 20 dB per decade. At certain moment we reach the frequency of the first zero, so then this becomes comparable to 1, and we cannot assume this whole term to be 1. And then what you see is that the minus 20 dB per decade will be compensated with plus 20 dB per decade due to the 0, and they will cancel each other, so it will have a total of 0 dB per decade. This will be a negative 0. In this example it can be also a positive, but in this example it's a negative 0, and then the phase rotation is plus certain degrees from 0 to plus pi from 0 to plus pi over 4 over 2. So basically also the phase rotation is compensated. If there was here a different sign and we had a positive 0, then the phase rotation will be also negative, but in this example it's positive. Then we reach again the second pole here. The frequency is 1 over dB, and then this term needs to be taken into account. We have again minus 20 dB per decade, and the phase is rotated negatively. We reach again the next 0, tau over 2, and in this way we constructed this exemplary exemplary Bode plots. To conclude, let's consider now this example. A linear system is given with 2 poles, negative real poles, and 1 0 in the origin. And let's try to sketch the expected Bode plots, the magnitude response and the phase response of this system. So here I will draw say this is H. This will be here. We'll draw the magnitude response, and the phase response or the phase shift will be here in this plot. So we have here low frequencies and we have here high frequencies, from low frequencies to high frequencies. To evaluate the low frequencies, we consider then frequencies that are close to the origin. So exactly at the origin, the signal will coincide with this 0, and the transfer will be 0. Yeah. As we move away from the 0, then we feel less the influence of the 0. Hence, the transfer will increase. Until we reach this point, omega p1. So this will be the frequency of the first pole. Here. Up to this moment, the frequency increases by a rate of approximately plus 20 dB per decade. At this moment, the distance between our frequency that we evaluate and the 0 and the first pole become comparable. So then this plus 20 dB per decade will be kind of compensated with the minus 20 dB per decade due to the pole. Keep in mind that then the transfer will be something like Z divided by P1. Yeah. So here in this region, what we will have is that it will be 1, because any delta in Z vector and any delta in ZP will cancel each other in this region. Here in this region up to this will follow the Z vector, the increase of the Z vector. Now, say we reach here the second pole, P2, omega P2. And now the vector will be Z, P, P1, P2. P1 will cancel with the Z vector, and then the transfer will be governed by 1 over P2. So this will be then minus 20 dB per decade. This means that now we can predict the amplitude transfer of this system, and this will be a bandpass filter. So at very low frequency we will have attenuation due to the zero, then we will have a pole, we will have a bandpass, and then we will have again a stop band due to the second pole. So there will be high pass characteristic, then band pass, and then low pass. And this will be given by the two poles. Now let's say something about the frequency, the phase transfer. At very low frequencies, we have the plus 90 degrees due to the beta. So basically it will be, the transfer will be governed by angle beta minus angle alpha 1 minus angle alpha 2. Yeah? So this will be beta due to the 0, and it will be 90 degrees, or pi over 2 minus the angles alpha 1 minus alpha 2, and the alpha 1 is this one, and alpha 2 will be this one, then depending on the frequency that we evaluate. For very low frequencies, alpha 1 and alpha 2 will be almost 0. So this means that our transfer will start from simply pi over 2. And then at the pole frequency, we'll have this influence of 45 degrees due to alpha 1, and we can assume that alpha 2 will be very, very small. So we'll have so we'll have 45 degrees, pi over 4. All right, here. Then the phase will continue falling, and here at this frequency what we'll have is minus 45 degrees due to, so this will be this frequency, so this will be minus 45 degrees, and we can assume that the alpha 1 is 90 degrees, minus 90 degrees. And here we have the 90 degrees of the beta. So at omega p2, it is at this frequency, so we have pi over 2 plus pi over 2 due to the 0, minus pi over 2 due to the first pole, and minus pi over 4 due to the second pole. So the characteristic will come here. Yeah? The phase characteristic. And then at very, very high frequencies, the minus 90 degree rotation due to the second pole will be completed. So this means that at very high frequency we will have minus pi over 2, minus pi over, so we will have simply minus pi over 2. And then the characteristic will be something like this. So we will start from pi over 2 plus pi over 2 phase rotation. Then at the center frequency here will be exactly 0, because at the pole will be about pi over 4. At the second pole will be approximately minus pi over 4, and then at very high frequencies this characteristic will be minus pi over 2. So now we can give our answer that the given combination between poles and zeros produces a bandpass filter. First, we have a stop band, because at very low frequencies will be very close to the zero, and then there will be attenuation. As we increase the frequency, we will reach the first pole, where the effect of the zero will be cancelled by the first pole. Then there will be a pass band if we continue increasing the frequencies until we reach the second pole, and after the second pole the characteristic will start declining again. If we look at the phase, at low frequency the phase will be rotated by pi over 2 due to the zero in the origin, and then as we increase the frequency we will start feeling the effects of the two poles, first of the first pole and then of the second pole. Each pole will rotate by a total of minus 90 degrees. So at the center of this pass band, the rotation plus 90 degrees due to the zero will be compensated by the rotation of minus 90 degrees due to the first pole, and at very high frequency the minus 90 degrees of the second pole will be added and will be dominant. In this approach you can evaluate any linear system for any given combination between zeros and poles. So thank you very much for your attention.